hopefully at this point you understand the concepts of limits a little bit more, right? And that the limit is the value that a function is approaching as x approaches a given value, right? And hopefully that makes sense to you. And so what we're going to do now that we've talked about a limit and how to evaluate limits with graphs, is how can we do it if we don't have a graph? Okay, and that's our topic in these next couple videos, evaluating limits without graphs. Okay. Hopefully you remember that as we were doing these, we had different techniques for evaluating limits. Going back to what we said, remember the different techniques. We had the graphical analysis we could use, and then table of values. But if we don't have either of those, then we can plug in to the function if it's continuous at the x value or the domain restriction is reduced out. So that's what we're going to focus more on this. Let's try to plug in. And we've done a little bit of this in our graphs before, right? And so now let's do it full force. Okay, so example, evaluate each limit. Okay, so let's see, the first one we'll do is this. So if we're looking at this one, and let me, okay, good, focused. If I'm thinking about what happens at 3, from the previous video we talked about that if nothing special happens for the function at the value where you're evaluating, at the x value we're evaluating, this is a c value, just so we know. Okay, if nothing special is happening at that c value, we can just simply plug that in and evaluate our function, and we would get 17 for this one. Okay, we could create a table of values to verify that, but if we think about it, right, as you're going to be plugging in values that are approaching 3, right? So if it's from the left, it'd be like 2.9, 2.99, 2.999. And from the right, it's going to be 3.1, 3.01, 3.000001. Okay, multiply it by 5 and then add 2. We're going to get progressively closer to that 17. And you could just look at a table of values to verify it, but I think hopefully at this point that makes sense to you. So just doing a straight plug-in, right? So in this case, we know the function is continuous at x equals 3. So we can plug in to evaluate the limit. Because it's continuous, this graph, it's a line if I were to graph it, right? Because it's a line, right? At every single point that we have, the limit equals the actual value. We never have to pick up our pencil point. Okay. So, right, there's plenty that are like that. Sometimes you might, have a directional limit there. So let's say we're going to do 2 from the left of 4x minus 1. Okay. And if we're thinking about as we approach from the left of it, okay, as we approach from the left, I'm going to be plugging in 1.9, 1.99, 1.9999999, timesing by 4, and then subtracting 1. Right, so basically, I'm practically plugging in 2 for ourselves. And I'm just practically plugging in 2. And so 2 times 4 is 8, right? Minus 1 is 7. Okay? So basically, this value is practically 2. We're going to multiply it by 4 and then subtract the 1 to give us that 7. Okay. Okay. Sometimes, all right, you might have something similar to that, and in this case here, x is approaching negative 2. Oh, so basically, it doesn't matter that it's only approaching from the left. It's just the same. So the left, the limit as you're approaching from the left, right, is the same as what the value actually is at 2. So we can just plug in 2 to get our value there. Okay. So let's say we have this. Okay. Right. If we're thinking about this one, this has a domain restriction. The domain restriction here is at x equals negative 4, right? But we know that everywhere else, if we think back to the graph we just did, the reason we did all the graphs is to help us to visualize this, right? This graph, the asymptote is going to be at negative 4. Okay, the y-intercept is going to, the horizontal axis is going to be at 1. So basically our graph is going to be something like this. for ourselves, okay? At every point other than -4, there's nothing special happening to the graph. The graph is nice and smooth and continuous there. Okay? So at -2, nothing special is happening to the graph. It's just passing right through. And we saw that in some of those graphs we did on the other ones. And so we can just plug in the -2 for ourselves. The top here is approaching -2, and the bottom is approaching 2. Okay? With limits, you can evaluate each piece individually and just divide them. So the limits are really kind of flexible in how we do it. So basically evaluate the limit of the top, divide by the limit of the bottom, right? And we get -1 there. Okay? So that is the same as the actual value we'd have. And so that's why we can just get -1 there. Sorry for the interruptions. I have to keep having to pause it because it's been there's a little action going on here. So, okay. Let's see. So, we have those rational functions. So the same thing would happen, even if I'm doing a directional limit. Let's say I'm approaching 1 from the left of x over x plus 1 here. Okay? Nothing special is happening at 1. There's a domain restriction at -1, but not at 1. So I can just evaluate this by saying, okay, the top is approaching 1 because it's just x, and the bottom is just approaching 2, so it's 1/2. Okay, it doesn't matter that it's a directional limit there. Okay, so all of these are pretty straightforward type limits. Okay, we could, if you're saying to yourself, how do you know that's true? I could graph it out, sketch the graph, and see that that goes that way. I could do a table of values. I can plug in like 0.9, 0.999, 0.99999. That's what we did when we first did limits, and we saw what it approached. Okay, we're trying not to do that every single time. So, all right, we're just looking for our shortcuts here. Okay, let's say we have some trig. Okay, because you might have trig functions there to deal with. Okay. Okay. And what do you first do? It operates on the same principle of, is this function nice and is there anything special happening at that value of pi over 3? And if we think about the graph of sine, and I know that the periods change, but there's our relative graph, our sketch of graph is pretty much going to look like this. And yes, it's going to get squished down or whatever, but it's pretty much going to look like that, right? And we can see that you're never picking up your pencil point at every point there. Whatever the value is the same as the limit that it's approaching from the two sides there. So it's pretty safe on the sine to just plug in the pi over 3 for ourselves and not have to like make a table of values. Right, so you do sine of 2 pi over 3, right? So it's a 60-degree angle. So sine is going to be √3 over 2, and we're in the second quadrant, so it's just √3 over 2. Okay. Now, if you're doing trig functions that have asymptotes, okay, that's going to be different, right? We'll do that. We'll do that next week. Okay. You totally can have that, and we'll take a look at it. But we've done enough analysis. You probably can envision what's happening. We're just going to skip those for now. Okay. So we just keep that in mind. Like all of these are like, right? Yeah, they're different functions, but nothing special is happening as we're approaching that value we're going to deal with. Okay, so what are we going to do then if we get something like this? X approaching -3 of x plus 3 over x squared plus 4x plus 3. Okay, so let's think back to what we did last week with our graphs, and that's going to help us here. Okay, so if we look at this, let's figure out what our domain restrictions and see if this x value that we're approaching is going to be a domain restriction. If I factor this out, I can see that I can reduce this, so it becomes 1 over x plus 1, and that's with the condition that x, is not equal to -3. Okay. So what do we see happens here? Okay, so if we had plugged in -3 originally, it would have given us 0 in the denominator. It also would have given us 0 in the numerator. Right? 0 in the numerator, 0 in the denominator. And we can see that the 0 over 0, when you're doing it, means you're missing something. Nope. What do we mean by you're missing something? That means there's got to be some kind of trick to do it, some reducing. Right? So reducing or a shortcut, because there's going to be some that have shortcuts. And you just use that shortcut, and I can figure it out for you. Okay, and if we plugged in this at the beginning, I would have gotten 0 on top, 0 on the bottom, 0 over 0, right? That's the sign that, hey, there's more than 2 meets the eye. Now, if I use the reduced version, you'll see that if I plug in -3, I don't have that happen anymore. And why is that? It's because this discontinuity, if we think back to it, we can still evaluate the limit, because as we're doing it, I should put the limit right here. All right, by putting that limit there, I can get rid of this piece right here. Okay? And if I'm going to evaluate the limit, the top is just 1 all the time, but the bottom is approaching -3 plus 1. It's approaching -2 for the denominator. My overall limit is -1/2. Okay? And if we think back to the graphs we did last week, this would have been one of those holes, one of those open circles that we'd have in our graph there, because the domain restriction reduced out might just give us a hole. Okay. So, now, if you reduce it like that and you still have a domain restriction, that's going to be a vertical asymptote. Yes, we've figured out how to do those. You're just not going to see them this week, and that will be part of next week's work. Just the way that these worksheets are broken up, it's not there yet. Although I know you guys could figure that one out. Okay, so you still could have directional limits as you're doing this. Okay. If I were to plug this in right away and say, okay, the top is approaching 0, the bottom is approaching 9 minus 15 plus 6, okay, the bottom approaching 0, I get that 0 over 0 again, okay? That tells us that this must reduce, or there must be something we're missing. It doesn't tell you there's definitely a limit, it just tells you that like you have to do some more work here, okay? So let me try to factor the denominator. The denominator, if I factor it, is x minus 3. And x minus 2, yep. And the top, well, obviously, it doesn't factor. Okay, so this limit is equivalent to this limit. Okay, now notice I don't have to write x not equal to 3, because remember, limits don't care what happens at a particular point. They just care about our trends. Right, so we're just thinking about the trend in this graph. Okay, and this graph here trends to, well, the top is always 1, so it's no trend there. The bottom 2.9, 2.999, 2.99999 minus 2. Okay, this is trending towards 1. So my limit is 1. Okay. Quick notation thing, it is after you reduce it, you must write this limit here again. It has to come along for the ride. Okay. You should really be writing it every single step as you go through reducing. You should be writing this. Okay. That's what they're looking for, your teachers next year, or in the AP exam will be looking for, that you write that out. Okay? If it's a multiple choice, then it doesn't really matter, but if it's open response, that's critical. Okay. So, other types of problems, right? Oops.